introduce our speaker for today. Dean Henry Brady is the Dean of the Goldman School of Public Policy and holds the class of 1941 Monroe Douche Professor of Political Science and Public Policy at UC Berkeley. He received his PhD in Economics and Political Science from MIT in 1980. Dean Brady's research interests are in electoral politics and participation, social welfare policy, political polling, the dynamics of public opinion, and statistical methodology. He has authored or co-authored 10 books and numerous articles, over 80, and has received a number of honors and accolades for his critically important work. In addition, he has worked for the Federal Office of Management and Budget and other organizations in Washington, D.C. Dean Brady is the past president of the American Political Science Association, past president of the Political Methodology Society of the American Political Science Association, and past director of the University of California's Survey Research Center. He was elected as a fellow of the American Academy of Arts and Sciences in 2003 and a fellow of the American Association of the Advancement of Science in 2006. Please join me in welcoming Dean Henry Brady, who is here today to talk about big data, machine learning, and data science for policy in California, prospects, possibilities, and limitations. Thank you.
Great, thank you. Thank you so much. This is working? We're working, good, good. So I have to start by telling you a story. So we had a dinner party one night, and my wife asked me to invite a bunch of my friends, which was kind of her. And I invited a bunch of people. And then she said to me, why are these people here? Why are they going to be invited? And I said, they all love data. Her eyes rolled. She was sure this was the formula for a disastrous dinner party. It turns out we had lots of fun because we all loved data. I have spent a career loving data. That's not the person who's on Star Trek, by the way. That's data, the actual information, the bits and the bytes. And I also realize now that all my life I've essentially been a data scientist, which reminds me of a conference I went to in the early 70s, the American National Association of Secondary Materials Industries, which is a recycling conference. And there was a man who got up, and this is right about the time that Earth Day was beginning and the environmental movement was really getting underway. And he got up and he said, all my life, my children have been embarrassed by me. I was a junk man. All I did was collect junk and sell junk. But now I'm a recycler. And my children approve of me and respect me. Well, I feel a little that way about data because it didn't used to be that being a data scientist was something that was really hot and exciting, but it is now. So now finally my children, well, they don't actually, but what the heck? You can't win them all. They still know who I am and can laugh at me at inopportune moments, but they know me too well. So let me just try to get through a lot of material here today, probably too much to really go into as much depth as I would like, but I really want to give you a taste for this whole field, and that includes an overview, some sense of how data and information are changing society, and finally a bunch of different examples. And I don't know how many I'll get through, but I just really want to show you what we can do with big data and data science. So these are the things I want to do. I'm not going to go through the list, but I want to do nomenclature and the information age, how we got here, defining big data and data science and artificial intelligence, then really talk about the limits. This stuff really is sexy right now. So you say, I'm using artificial intelligence, and that sounds like you're doing something so super cool. Turns out a lot of artificial intelligence methods are nothing more than stacked logistic regressions. That sounds a lot less exciting than artificial intelligence. To put it another way, a lot of stuff that statisticians have been doing for years, the junk men, what the junk men have been doing for a long time is what's now called artificial intelligence and is exciting like recycling. So it's really important not to be overwhelmed by these folks or too impressed by them, and to understand there are real limitations to what you can do. Okay, so nomenclature. These are just some terms. What are big data? Well, large collections of digitized data. I'm going to talk a little bit more about this in a minute. Data science. methods of analyzing those data, artificial intelligence, computer methods such as visual perception, speech recognition, decision-making, language translation. But as I just said, these are actually many standard statistical methods that have been around for years. You can translate all of these methods into standard statistical methods. So if you think statistics is boring but artificial intelligence is exciting, you're a little like the junk man recycler problem. They're really the same thing. And then cyber infrastructure, which is actually a term I like. The reason I like it is because in 2006, I wrote this report for the National Science Foundation with Francine Berman, who's a computer scientist. And this was all about how cyber infrastructure was going to change the social sciences. And I've read it recently, and actually a lot of what we say has come true. It's a really sort of nice report, but it shows you that 14, 15 years ago I was thinking about these issues. Okay, I want to talk about the information age. This is a really quick overview, but what's happened in the last 150 years is we've gone from being a society in which the major changes were about energy and industry, so the steam engine, the gasoline engine, to really an information age, where information is what really is propelling a lot of innovation. We started in the 19th century with telegraphs, telephones, and emails, which are all person-to-person kinds of approaches. These came along at different times, obviously. We started with the telegraph. Then mass media, that's a source-to-many method, where one source communicates with many people. Then computational power came along. That allows us to manipulate data. And finally, networking comes along, which connects groups. Behind the information age having the impacts it has today is the fact that we've gone from analog to digital representation of information. I'll explain that more in a minute. First, just the time periods. Notice we start with telegraph, telephones, then we go to phonographs, which are mass media, cinema, radio, television. Mainframe computers come along to manipulate data. Then personal computers, which allows a decentralized computing. Then the internet and World Wide Web, which actually combines these things. We get point-to-point, mass media, and networking. And then finally, down at the very bottom here, smartphones or tablets and things like that, which are point-to-point, they're mass media, they're computing, they're networking. They're all of these things put together. Really quite a remarkable invention, what we've got in this cell phone, which is a lot more powerful than the supercomputer I worked on when I started programming in 1967. It was a CDC 6600, for those who are aficionados of various computing machines. 60-bit word length, cooler than IBM. Okay, so things have really changed and stuff has come together. This is a picture I've lifted from a really great study by Hilbert and Lopez about the growth of information. And one of the things that's happened, this is time down here. These are years, and the years somehow got obscured. Oh, no, there they are. 86, 93 to 2000, and all the way to 2007. And what you see is there's been this opening up of more and more information, a deluge of information. So much information that it's impossible to keep track of it all. But maybe more importantly is it used to be analog. So analog is like a vinyl record, where basically the way it reproduces sound is there's bumps in the grooves, and the needle gets those bumps. That makes the needle vibrate in a certain way. And so in some sense, the bumps reproduce speech or singing or whatever else. So that's an analog representation. What digital representation does is it converts anything into zeros and ones, bits and then bytes, which are bunches of bits. And what you see here is it used to be almost all analog storage. Things like tapes or cinema, what's a cinema? Historically, it's been little pictures, lots of little pictures. Now we digitize that. So everything now is becoming digital. That's important because what it allows us to do is to have sort of a common lingua franca for everything. Now, it still turns out there's a babble of different languages out there, but there's at least a common way it's represented in bits and bytes that allow you to take bits and bytes in one language, like ASCII, again, for those who are aficionados of the the history of this field, and converting ASCII into EBCDIC. So what are the features of the information age we live in? The volume has increased enormously. That's the fanning out. The velocity has increased enormously. We see that every day. The variety has increased enormously. Lots of things are digitized. Cell phone video, podcasts, government data, transactions data, everything is digitized. And then finally, a fourth thing, which has become really apparent since the 2016 election, is we got a problem of veracity. And now we got the deep fake problem, where somebody can make a video of me, seemingly me, saying all sorts of outrageous things. I think these four trends, so this is sort of physically what's happening. There's a lot of volume and velocity and variety, and now this question of the truthfulness of it. I think these are the things, though, that are more structural and deep-seated about what's happening. One is I came up with this terrible neologism. I apologize for it. Datafication. Everything has been datafied. So you get on the web and you do a transaction, there's data. You are in a building here, I'm being filmed right now. There are video cameras all over the place that film people in many cities in the world. So many of us are turned into digital data. And you could call this just digitization, but I think it's more than that. It's datafication. Everything's become data. That in itself would be a big deal, but what's even more important is the connectedness. We can now take data of various events and connect it. We can connect it through the names of the persons if we have that. We can connect it through the URLs if we've got that. We can connect it through the geolocation if we've got that. We can connect it through face recognition. On the news this morning, there was somebody who's got a face recognition program. It's harvested billions of pictures from the internet and can identify people by matching a current photograph with all this other information. China is going in this direction, for example. So we can connect these things. And sometimes we have a bunch of these different pieces of information. And it turns out there's statistical theorems that show that very small numbers of information, small bits of information, allow us to figure out who somebody is. And then there's networking. This is something more than just connectedness. This is people creating networks. So a tweet hashtag is a network of people. A Facebook page is a network of people. And so these groups are self-forming. So it's not just point-to-point communications. It's not just mass communications. It's networking communications where the networks are created to some extent, although not entirely all the time, by the people who are authoring those Facebook pages, or authoring the tweets. And then finally, the most amazing thing we have is if you go back to Claude Shannon, who wrote the book on information in the 40s, he was concerned with this problem. How do we send information from one place to another and make sure that the result at the end is the same as the result at the beginning? So he was talking about verisimilitude. And a lot of information science is about how do you make sure that with a minimal number of things sent, you can get the message sent correctly. And so we get checksums and all sorts of different methods that we use for that. That's not all that we're doing now. Now we have situations where we go into Google and do a search, and basically Google is individually authoring for us a reply based upon the characteristics Google has on us, and it has a lot of information on us from past searches and other sources, and based upon information it knows about lots of other people. So it authors for us an individualized response, and it does this immediately. So this authoring is something brand new and hard to actually get a fix on. Okay, big data. What are big data? Well, I don't like the term big data that much. It's one idea is it's a challenge to existing technology because it's so big. Well, it used to be when I did computer programming in the 60s that a 600 kilobyte file was a big file. Now it would be 600 terabytes probably, or something like that, which is a lot bigger file. So in effect, this is a moving target. because technology keeps improving. I think it's best described by the trends noted above, that everything's datafied, it's connected, it's networked, it's authored, and that we really have immersive data. That's what big data really is. We're immersed in this sea of data, and that's changing our lives in fundamental ways. Types of big data. There are lots of types, but here's a typology of 4 types. Administrative data, which is really predominant in a lot of government agencies. It's very important data to have. It's typically the data of record. It's like the people whose checks were sent to them for a given program. That's the data of record. It's got some problems I'll talk about in a minute. Internet data, you know what those are, all the data on the internet. Textual data, more and more, is something we can deal with in a way we never could before. And there's tons of that, like the entire corpus of all the stuff written by the ancients. People are working towards digitizing everything that we have from the ancient world that was written. And then you can do incredible searches through that material and maybe find things you never found before. And then sensor audio and video. This is a bit of a grab bag, because maybe I should have broken these out. But sensor data, like from satellites or from ground-based sensor systems or from LiDAR or something like that. Audio, you know what that is, and video. These types of data are complicated because often matching them with the other kinds of data takes some steps. Okay, let me give you examples. Here's administrative data. This is something I did in around 2000, which is to do a study of the 50 states, and we asked states to tell us which data sets they linked and whether they linked them over time. So this is Child Protective Services, foster care, Medicaid claims, child care, etc. And across the 50 states, we found out that there was a lot of linking going on, and basically the way we've done this is the further apart the circles are from the center, the less likely they are to be linked. So the stuff near the center is more likely to be linked. For example, the unemployment insurance earnings base wage file is often linked with the AFDC, TANF, whatever the name of the welfare program is, data, and so forth. Jobs data is often matched with that. This is 20 years ago, so this has changed dramatically. Also, within each circle, there's a percentage, and that's the percentage that's linked over time. So once you've linked these data over time and linked them across programs, you're linking them intensively and extensively, and you know a lot about the people in those files. So that's administrative data and shows how you can make it more powerful by linking, both temporally or across programs. This is some internet data. This is a study that I think is quite remarkable. An economist looked up and got data from Google on where people had searched for the N-word. By the way, when I was in high school, I was taught about the Scarlet Letter, and I had no idea what the Scarlet Letter was about. But I'm presuming that everybody knows what I mean when I say the N-word. And I don't want to say it, but it's important to, I think, understand its importance in American politics, and this study shows that. So he looked where had there been searches, more than large numbers given the population, for the N-word. And by the way, the thing that's usually searched for is N jokes, which I think makes it doubly despicable and distressing. And then he said, okay, let's link these data geographically to election returns, 2004, when John Kerry ran against George Bush, and in 2008, when Barack Obama ran. What he found is that it looked like there was a loss of about 4% of the vote due to racial animus. If you believe that people who search for the N-word are more likely to exhibit racial animus, it looks like those folks were less likely to vote for Barack Obama. What's interesting about this is it tells us something about the importance, sadly, of race in America. It also tells us that we can use things like the internet to do an unobtrusive measure of racism. By that I mean, we on surveys often ask people if they're racist, and we try to do that in subtle ways. But the truth is, people aren't stupid. They know what we're asking, and therefore they may misrepresent what they are thinking and doing. In this case, This is just something they got on the internet, and they searched for this. So we now have this result, which is, as I say, distressing, but I think tells you something about America. By the way, the more red, the more such searches were occurring. Okay, this is another extraordinary study. Textual data on the internet. So this is textual data. Chinese censorship of web posts. So Gary King and his team, Jennifer Pan, Margaret Roberts, at Harvard, found a way to quickly search every day Chinese websites and look at their content using analysis of textual data. So they had machine learning ways of analyzing the data to figure out what topics they were on. And then they'd follow those web page posts and see if they were censored. And what they found, surprisingly, was that it wasn't censorship of criticism of the regime. A lot of these stories down here on the right are folks who were criticizing the regime or making essentially political statements. And they were on the lower level of censorship. Censorship increases as you go to the right on this scale. The ones that were censored were ones that were advocating collective action or some actual action that might undermine the regime. So the regime was more concerned about collective action than it was about criticism. This was a new finding, and it was a surprise to folks. You would have thought that they would have just censored anything negative about themselves. No, they don't do that. So this is another extraordinary study. And then finally, I'm going to talk more about this study. GRACE is the Gravity Recovery and Climate Experiment. It's a set of 2 satellites way up high, 137 miles apart. They use gravimetric techniques to figure out variations in gravity, which tells them how things are changing on the ground over time. So if you drain an underground aquifer, that changes the gravity in that area, and you can see what's happening. So this is terrestrial water mass trends over time, with red being worse. But more importantly for us in California, here's the Central Valley during the drought years of 2011, 2012, 2013. And you can see what's happening. The Central Valley aquifer is going, red means less water. It's being depleted during that drought. So that tells us we got a public policy problem. And it's astonishing technology, you think about it. It's just variations in gravity. Okay, data science, the classic definition is that we have computer or hacking skills, statistics, and substantive expertise. And what makes it go beyond just statistics is it is computer science, and it is substantive expertise. So I argue in a paper I wrote, and I take this from various sources, that in fact it's all these things coming together that constitute data science. So data gathering is the first step. That's actually something that the substantive fields have to be involved in. The substantive fields know how to collect data on water or on racial profiling or on other issues. So you've got to get them involved at the beginning. Computer scientists are maybe good at putting the data in some form that you can maybe then go and use it, or transforming it. The data modeling is statisticians. Data visualization and presentation is media laboratories on campuses. And then data archiving, indexing, search, and governance, library and information schools. So this works across a lot of different parts of the academy to form a new discipline called data science. Okay, artificial intelligence and machine learning. Well, this is a model of those stacked logistic regressions I was talking about. Basically, features, information on features comes in here. You do these regressions, logistic regressions, and you do multi-layers. The more layers you have, that's called deep learning. Turns out it works really well. Turns out nobody knows why. Actually, some fascinating papers that have been written about maybe why that's so. But it turns out it's very good at things. So to give an example, how do we classify an animal as a dog or cat? I'm going to make this really simple because please understand that these techniques are really simple fundamentally. There's nothing really magic about them. If you know features of a dog, of an animal, you can try to figure out if it's a dog or a cat, and that's all these techniques do. So how about features like, is it large or small? Does it bark or not bark? Remember, by the way, there's some dogs that don't bark, so you could make mistakes here. A tail or no tail? White or non-white? Meow or no meow? Well, if it's large with a bark, tail, non-white, no meow, I call it a dog. If it's not large, no bark, tail, non-white, meow, a cat. Now, some of those features are diagnostic. The non-white is not particularly diagnostic, but the meow bark is very diagnostic. And what machine learning does, or artificial intelligence does, is it says put more weight on the bark meow issue than on the white non-white. That's all it does. Okay? So that's, now you know you can do machine learning. You've gotten the course in it. So here's deep machine learning with lots of different levels, and it takes a picture, turns it into pixels, uses the stacked regressions, and ends up with it's a chihuahua. So easy. Okay, and it turns out basically this is pattern matching. It's something humans are pretty good at. We learn from childhood to pattern match. Is that a dog? Or is that a cow? Is that a cat? Here's a hint. It goes meow. Oh, that's a cat, says the child. We can use it for symptoms and diagnosis of disease, features of the road ahead, and safety for proceeding, and on and on. Not going to read them all, but just lots of pattern matching problems out there that are important. However, the limits of data science. Here's computer classification mistakes. Okay, that's a school bus. This is a business. And that's a starfish. In each case, those are mistakes. Now, why did the computer make that mistake? Well, okay, that's a school bus. And notice, it looks a little like that pattern. And by the way, the computer had in its memory that there was a sign for a business called Red Devil. Therefore, this must be a business. And finally, the starfish, I guess it looks a little like the squiggly stuff. So mistakes can be made. So what are the dangers? The dangers are the training set matters a lot. So the way you figure out whether the technique is going to work or not, or to make the technique work, is you have a training set. It's a little like if you teach your child wrong, and you say, oh, cows go meow, your child will make a mistake. We used to own a Dodge Caravan. My son, one day, we were driving along, he was very young, and he sees a Dodge symbol. And he says, Mom, Dad, a Dodge Caracar. In some ways, that was brilliant. That was really smart. But he was wrong. It's not a Caracar, it's a car. It's a Dodge car. But we had a Caravan, so it must be a Caracar. So, and he called, by the way, the kitchen was the chicken. Kitchen, chicken. I mean, these are the mistakes children make. You all have these stories from children in your life. These machines are not smarter than children. Okay. So the training set problem is a problem. If you're training it on the wrong things or training it incorrectly, it's going to mess up. Second, it's better at prediction than at causal inference. Prediction is when you take a trend and it's going to say it's going to be like that tomorrow. Prediction is like what I did in 2016 and said it's not going to be Donald Trump as president. I didn't think of causal factors like the fact that the heartland of America had been hollowed out and there was an opioid crisis and there were a lot of very upset people in states like Pennsylvania, Michigan, and Wisconsin. And I was a bad pattern recognizer then and made a mistake. I did, by the way, actually go around before the election and tell people they needed to take Trump voters seriously. So I felt like I got partial credit. Anyway, and then it's not good at the novelty problem, which is a bit like the causal inference problem. If you don't structurally and fundamentally understand a phenomenon, then you're not going to be good at prediction. And if you're only basing it on past experience, novelty is going to really mess you up. Okay. And let's understand there's lots of things AI cannot do. It can't experience emotions. There is some thought that we won't actually fully have real artificial intelligence, until we embody computers within bodies that can feel things and that maybe have something akin to emotions. Because that's how we really fundamentally experience and understand the world. They're not good at analogies and models. Humans are really good at taking far-fetched analogies and using them to say something interesting. And computers aren't really good at that. And finally, they're really bad at developing causal thinking. They're good at prediction, but they're not good at causal thinking. There are some who think they're going to get there. Maybe, I don't know. I'm a skeptic. So there's real limitations. Okay, societal change in the information age. I'm going to do this as just a slideshow because I just want to go quickly through some areas that are changing fundamentally in the information age. First, cyber warfare is changing the way the world works. Second, I'm doing these very fast. This is a collection of advertisements put up by the Russians in 2016. My favorite, this is about Hillary Clinton. Satan, if I win, Clinton wins. Jesus, not if I can help it. And it shows Satan and Jesus arm wrestling. An actual photograph of them doing that, no doubt. And then it ends with, press like to help Jesus win. In other words, press if you want to have Jesus win, press, and then we'll take you to a website and you can get signed up for the Trump campaign. So these are just amazing things, but this is a problem we face. Smart cities. Smart cities are a function of three things coming together, I think. Digitized administrative data sets, sensors, wireless networks, video cameras, all those data, and finally internet data, which can be put together with that. So we can use Zillow to understand housing prices, connect that with maybe sensor data to understand traffic flows, and digitize the administrative data that tell us something about the neighborhood. And so we can put all this together and we can first understand better how our city works, and second, maybe manage the city better. Precision medicine. Here the idea is that it turns out that some experiments show that a drug doesn't work, but it may be the case that it actually works for some people but not other people. So if we could link the drug with the genotype and the characteristics of the person, we might be able to actually solve their problem and not make sure that we don't give it to the person whose genotype tells us it's going to kill them. So precision medicine is an attempt to say, if we have lots of data on individuals, at least their genotype, but other information as well, might include how often they really take medicine and if they're responsible and all those kinds of things. And then if we have lots of understanding of how things play out with different administrations of these medicines, we can match medical care better to people. And then media and politics, what's the role of the internet? I showed you the advertisements earlier. Obviously the media has fundamentally been changed by the internet. And we're still trying to figure out what the media will look like in the future. And then finally, robots may take jobs. Now, I have a quotation from a 1962 article that says robots are about to take, automation actually, is about to take all of our jobs. That's 1962. That didn't happen, and that's 60 years ago. So maybe it's not going to happen now, but certainly automation or artificial intelligence is changing some areas. Okay, so let me skip that. I want to go through some examples. First, Central Valley domestic water wells. How can we manage groundwater removal sustainably? So right now, there's an enormous number of people in the Central Valley and elsewhere in the state, but especially in the Central Valley, who use the aquifer there to get water. In droughts, this is a problem. This is a paper done by a bunch of graduate students at University of California, Davis. They came to a hackathon we had at the Berkeley Institute for Data Science, where I'm an investigator, and they won a prize for what they'd done. It is a super cool study, as you'll see. And it was done, by the way, I should say, along with the Department of Environment. No, I'm in the wrong place. Here, it was done by the California Water. Here it is. Governor's Office of Planning and Research, West Big Data Innovation Hub, Water Foundation, the Bay Area Council, and the State Water Resources Control Board and Department of Water Resources. So it was a whole bunch of people got together and said, let's have a hackathon and see what we get. And this was one of the studies. So here's the problem. Very, very simple. So this is the ground level at the top here on this diagram. The aquifer is the light blue. If the groundwater in light blue drops, the well on the left, which is a shallow well, is going to dry up. And the folks using that well won't have water. Why does the ground level fall? Nature, droughts and lack of rain, cause the ground level to fall. Another reason is people pump out the water. So the failure depends upon the depth of the well, the ground level fall due to droughts, and the pumping of water. So what did these students do? Well, by the way, here's what they're looking at, the Central Valley. This is a map of where the domestic water wells are in the Central Valley. Darker, more red means more of those wells. They took 3 kinds of data: location, elevation, and depth of wells from administrative records, from what's called the well completion reports, which have recently been digitized for a long period of time. They took groundwater levels from a website that provides this information, and then they got data on well failures by year. So basically, going to the next page, this is location, elevation, and depth of wells. This is changes in groundwater over time, where darker colors mean more changes. And this is time of well failure data in 2 versions. This is just little dots where each well failed, and this is colors showing you where there were concentrations of where wells failed on the right. Putting these data sets together, and by the way, I took this from a manuscript and I couldn't get rid of the watermark. They take the observed well failure data, use that with the other data to predict the well failures. And so what they did is showed they could predict pretty well the well failures, and that amounts to saying the map with the colors on the left matches the map with the colors on the right. They're very similar. And then they came to this conclusion that they could simulate what would happen if the drought had continued. So the drought ended by 2016, but if there were a continuous drought, you can see that you'd have more and more well failures. So to the left is actual observed well failures year by year, and then to the right of the dashed blue line is well failures that we would have had if the drought had continued, or if there had been an intervening winter with some rain, but then more drought. In either case, you can see it starts to almost exponentiate. We're losing a lot of wells. So this tells us we got a big public policy problem. Okay, I'm going to skip that. Let's do racial identity and police profiling. Is there profiling by police? Many studies have shown implicit racial bias. How do we figure out if there really is? There's the Racial and Identity Profiling Advisory Board 2020 annual report. This is a version of it. 2 of my faculty members, Steve Raphael, is on the board. Jack Laser was an advisor to the board. They contributed to this report along with dozens of others. This is what the data were that were collected. Each officer was asked to provide this information on each stop. It's information regarding the stop and information regarding officers' perception of the person stopped. Notice here, perception is really the issue. Using 1.8 million stops, we find who is stopped. Well, it's mainly Hispanics, then whites, then blacks, and so forth. But these alone don't tell us that there's any problem, because it depends upon the frequency of these people in the population. And you would presume you're going to stop more of a given group if there's more of them in the population. So this takes American Community Studies surveys, which are census data on the makeup of areas, and links it with the stop data geographically across the state, and shows that, in fact, more stops than population for Black and Middle Eastern South Asians, about same for Hispanic and white, but fewer stops than population for Asians. The trouble is, we still would like to know more. Should these people have been stopped is really the question, not exactly what their frequency in the population is. The question is, were they people who really should have been stopped because maybe they had contraband or something else? Well, it turns out you can get search yield rate, the number of searched individuals with contraband or evidence, over the total number of searched individuals. Higher search yield rates indicate that searches were successful. and resulted in finding contraband or evidence. Higher search rates suggest that there was a good reason to stop the person. Lower search rates suggest there might not be a good reason. So I'm going to skip to this one. Let's look at higher discretion searches. This is where actually the officer has a lot of discretion about whether he or she searches somebody or doesn't search somebody. We would expect implicit bias to have the biggest impact in this circumstance. And in fact, what we find, when officers have discretion, their searches of blacks and Hispanics yield less than those of Asians and whites. Yield less. That is to say, they do a lot of searches that lead to nothing. And that suggests that their discretion is being misused because they're searching people who have no contraband. And so this comes from the study and is, I think, pretty strong suggestive evidence, not absolute proof, but it's strong suggestive evidence of racial profiling being used in bad ways. So when officers conducted highly discretionary searches of individuals, officers had higher yield rates for whites than for all other racial ethnic groups. That strongly suggests some bias in searches because blacks and Hispanics were searched, but yields were lower. I have other examples I'm not going to get to, but let me just actually go through them really quickly. Better placement of polling places for voters is a study I did, and we're just going to go through very quickly all the data here. Sonoma County Dashboard for Social Services. It turns out the top 5% of the people getting social services cost the most money. And in fact, they cost 57% of the total funds in one county. So 5% of the recipients of services get 57% of the funds. Managing these cases better would really help maybe reduce costs and provide better services. So in Sonoma County, the California Policy Lab has put together, that's the thing that says that, has put together a dashboard that allows you to see who's getting what services. And that's what this is. You can look at the top half of utilizers, find out which systems they appear in, and what kinds of services they're getting. Predicting homelessness. Homelessness is really hard to predict. It's a needle in a haystack problem because so few people actually end up homeless. Turns out by using artificial intelligence, predictive analytics, you can actually find a way to do it. And it really hinges on the fact of putting lots of data together and finding out that just before the homeless period begins, people start using services at a really increased rate. If you look at the circle, the red circle, you'll see suddenly there's an upsurge in use of services. If you can get to them just before they go homeless, you may be able to intervene and help them. And there are programs to do that. So this is a real success. And then predicting water flow to improve dam storage. Why is this important? Increasingly with climate change, we need to store more water for longer periods of time. But when we do that, if there's suddenly a rainy period, we may have to release a lot of water, and we end up with damage like this that occurred to the Oroville Dam. So finding out how to produce better models, hydrological models, of water flow could help us manage water better. And so that is what this is all about. And do we do modeling? That is physical modeling of what's going on. Do we do data? Turns out modeling plus data is the right way to go, and we can really improve the way we predict water flow. We can better manage dams. We can have less dam failure, which is good. And so what are my conclusions? Cyber infrastructure is changing the way we run societies. We must wrestle with these changes, and I haven't talked about ethical issues, which are a big deal. But I do think there's tremendous opportunities for improving public sector decision-making by putting data sets together, using artificial intelligence, statistical methods, and actually being able to manage what we do in a better, more humane, and sensible way. Thank you.